So what we are really interested in is the entropy change for a process, specifically whether it is positive or negative. Since the states of matter have different entropies, the first thing to look for are changes in state. But what if there is no change of state? Can there still be an entropy change? The answer is yes. One way is for there to be a change in the number of moles of material ongoing from reactant to product. Take this reaction. 4 moles of nitrogen dioxide go to form 2 moles of dinitrogen tetroxide. This is a gas phase reaction, so there is no change in state, but there is a change in the number of moles ongoing from reactant to product. Since this is a balanced equation, the total number of atoms is the same on both sides. But there are more ways to arrange those atoms in 4 small molecules than in 2 larger molecules. In this case, there is a decrease in the number of ways to arrange the system. So there is a decrease in the entropy. The sign of delta S would be negative. If you're having trouble seeing how entropy changes here, consider this. I have 4 cards, numbered 1, 2, 3, and 4. And I want to ask how many different ways can I stack them on top of one another? I can stack them with 1 on top, then 2, then 3, then 4. That's one way. Or I could do 2, 1, 3, 4. Or I could do 4, 2, 1, 3. And so forth. You know how many ways we can do this? It's actually 4 factorial. There are 24 different ways to stack them together. But now let me bring in a couple of paper clips. And let me put 1 and 2. I'll stack 1 and 2 together, clip them together. Then I'll clip 3 and 4 together in this order. And now I'll ask how many different ways can I stack the cards? Well, there are only 2 ways. I can do it 1, 2, 3, 4, or I can do it 3, 4, 1, 2. The point is that if you take many small things and bind them to make fewer bigger things, there are fewer ways you can arrange them. So 4 smaller things have a larger entropy, more ways they can be arranged, than do 2 larger things. So let's work through a few examples. In the first, solid calcium carbonate goes to solid calcium oxide and carbon dioxide gas. We first look for changes in state. Notice a solid goes to a solid and a gas. Since a gas is produced, and there are more ways to arrange a mole of gas than there are to arrange a mole of solid, the product has higher entropy. The value of delta S is positive. The second example is the freezing of water. Although there is no gas involved here, there is still a change in state from liquid to solid. For a given compound, the liquid will have a higher entropy and the solid will have a lower entropy. The value of delta S is negative. Our third example is the reaction of nitrogen monoxide with dioxygen to form nitrogen dioxide. In this case, there is no change of state. But the second thing we look for is a change in the number of moles. In this case, 3 total moles of gas on the reactant side go to 2 total moles of gas in the product. Since the number of gas molecules has become fewer, there are fewer ways to arrange the products, so the products have lower entropy. So delta S is negative. In our last example, solid silver chloride reacts with solid sodium to produce solid silver and solid sodium chloride. There is no change of state. Solid goes to solid. There is no change in the number of moles. 2 moles goes to 2 moles. In this case, we can't determine the sign of delta S. There may be very small changes due to differences in the crystal lattices of the solid, but our conclusion is that delta S is small, close to 0.